All right, so we have our different formulas here, and it's a good idea to try and commit these to memory to the best of your ability, but I gave you some tips the other day in dealing with it. And those, my advice is the x shouldn't go on the adjacent side to the angle, right? So avoid putting the x there whenever you can. Usually we want the a to go there whenever possible, okay? And if you stick with that, then you'll end up with the right set of functions to substitute. So some of the homework problems like this one right here say, hey, why don't you try this substitution? Okay. So I'm just going to double check to see if their advice is sound, and then we will implement it and see what happens.
What's number 7?
Good question. Which this is number 7, correct? Thank you. All right, so I'm just going to draw my triangle and confirm their suggestion. So I have x squared plus 16. 16 is 4 squared. So since there's a plus in there, the square root here must be the hypotenuse. So I know that the square root goes there based on the Pythagorean theorem. Then my choice is to put x over here, not down below, which means this number down here has to be 4. So that's the triangle that I need to try and solve this problem. Now, if that's my triangle, then their suggestion that x should be 4 tangent theta makes sense, because the tangent is opposite over adjacent. Okay. So that gives me tangent of theta is x over 4, or x is 4 times the tangent. That's good. So I like that. Dx then, derivative of the tangent is secant squared of x dx. Now,
tangent of theta, not tangent of x.
Oh gosh, I'm doing that again. Thank you, Sarah. Now, on the right side, these should all be thetas. Thetas, thetas. And then the other thing to consider is the cosine would be 4 over the square root. So that puts the square root in the bottom, which I don't like. If I want the square root in the top, I flip the cosine, which gives me the secant. So that means the square root in this case would be 4 times the secant. Secant is hypotenuse over adjacent. So that's the set of things I need for this substitution. So now I just go start throwing things around. I have a slight complication here. I have an x squared in the bottom, but we can deal with that pretty easily because we know what x is equal to. So we can just square it for the substitution. And the 58 gets pulled out. So rewriting this, I'm going to pull out the 58. And then I have the integral, so I'm going to put a 1 in the numerator. In the denominator, x squared is going to be the 4 times the tangent squared, so that would be 16 tangent squared of x.
Theta.
Theta, good job. And then the square root is really 4 times the secant of theta. And then dx is really 4 times the secant squared of theta d theta. So we get rid of anything that has an x, replace it with trig theta stuff, and hope it cleans up a bit. All right, let's see. What do we have in terms of our cleanup at first? Well, the secant goes into the secant squared, and the 4 goes into the 4. And rewriting that, it's going to give me a secant over tangent squared. So new page. I've got, let's see, we had a 58. Now we get a 16 in the denominator. And then we have a secant of theta over the tangent squared of theta. And let's see, I think I probably should try to clean this up some more. If I was going to do a U substitution on tangent, I would like to see secant squared, but that's gone because we canceled it. If we don't cancel it, that puts a secant in the bottom too, which is, I'm not happy about. Any thoughts what I should do next?
Substitution for tan squared.
If I do a substitution with tan or tan squared, I'm going to get extra stuff that's not going to work. Right. Yeah, so I would do some trig identities here. Yeah, so a u equal to tangent is a problem because then I would be looking for a du, which is secant squared, which I don't have at the moment.
Isn't there a trig identity with tan squared in it?
Yeah, tangent squared, is it 1 plus secant squared?
So you would do something.
Does that sound right? Let's look up trig identities. So there's lots of ways to continue because there's so many trig identities. He had a ton. So Pythagorean. So that would be secant squared minus 1. We could try that and see what happens. So I'm going to ignore the integral for a minute and just try and clean this up. So I could rewrite it as secant of theta over, let's see, secant squared minus 1. Which, yeah, we can't do much with that, so that doesn't help. So I don't think that's good. We could switch to sines and cosines. That might help. So let's see. Secant is 1 over cosine, so I'm going to have a 1 over cosine in there. Tangent is sine over cosine, but this is in the denominator, so it'd be cosine over sine. So that would give me cosine squared, because it's a tangent squared over sine squared. And it looks like that's going to give us something to work with here. So I'm able to cancel a cosine. Yep, I like that. So new page, we now have that 58 over 16 integral of cosine of theta over the sine squared of theta. And then we can let u equal the sine of theta, because then du will be the cosine of theta d theta. So then this becomes 58 over 16. Here is my whole du, so I get 1 over u squared du. So that'd be u to the negative 2. And what's an antiderivative for u to the negative 2? Nope.
Negative u.
You add 1 to the power, so u to the negative 1. Yeah, and then we're missing a multiple of negative 1, so I'm going to say it's going to be negative 58 sixteenths. Yes, I know I could reduce that, but I don't really care yet. And then I'm going to get u to the negative 1, which would be 1 over u. And then we have to go back and substitute a couple of times. U is really sine. So I get negative 58 sixteenths times 1 over the sine of theta plus c. Then we have to go back to our substitution to figure out what to do with the sine of theta. So let's see, what should the sine be according to this triangle? X over the square root. Now we have 1 over the sine, so we would want the square root over x, right, if we flip it. So we get negative 58 over 16 times x, let's see, Squared on top, thank you. X squared plus 16 in the square root. X on the bottom, because we have 1 over sign, plus C. So that should be the antiderivative here. I was excited. Let's see what my open math thinks about that. So negative 58 over 16 times the square root of x squared plus 16 over x, and they added the plus c for me. Very much. Does that look right? That looks right. Ooh, we got a check. All right, let's try another. What else looked exciting? Ben recommended something that they're in. That one. Too bad. X to the 4th power. That looks interesting. Let's try that one. All right. So I'm going to consider that to be x over square root. The 4th power is x squared, and the 25 is 5 squared. And so building my triangle based on that,
What number is this?
this is, I think, number 9. Question. Number 10. So let's see, I have a plus going on, so that means it's the hypotenuse. So over here, I get the square root of x to the 4th plus 25. And then we don't want to put the x on the adjacent side. So on the opposite side, it turns out it's an x squared, not an x, right? It's the thing being squared. And then down here goes the 5.
Square.
No, it's actually the side length. So it's the thing that is being squared.
Okay.
Yeah, the x to the 4th gave us a little complication, so we get an x squared there instead of just an x. Okay, so that's a little weird. But we can still make a triangle based on it. All right, once I have that triangle, then it's kind of like before. The easiest function to make for trigonometry would be the tangent of theta is x squared over 5. So x squared is equal to 5 times the tangent of theta. This is where things get interesting. The dx is going to be a bit of a challenge because of the x squared there. So I think what I would like to do is rewrite that as x equals the square root of 5 times the tangent of theta. See if this works. And then dx is going to require the chain rule. So need a little space. Dx is take the derivative of the square root. Well, that's the power 1/2. So that's going to be 1/2 times whatever was inside 5 tangent of theta to the power negative 1/2, right? Because we have to drop the power by 1. And then we have to multiply by the derivative of 5 tangent, which would be what? 5 secant squared. D theta. So I think we have everything we need to make the substitution. I'm going to shrink this a little bit so I can try and fit that underneath. Oops. There we go. It's a little weird, but it'll work. All right, so let's see. Piecing this together with our substitution, the x is going to be the square root. So I'm going to have the integral, and I'm going to get the square root of 5 tangents of theta in place of the x. Dx is this fun thing. So let's see, the 1/2 I could pull out, the 5 I can pull out. So I'm going to pull out 5/2 for now. The negative exponent on the 1/2, what does that mean that's for us to do? Negative means the bottom and the 1/2 means square root. So this part right here means that there is a square root of 5 tangent in the bottom. Ooh, that's lovely. Look at that. And a little nice cancellation there. So I got that covered. I got that covered. I got the 5 covered. I have a secant squared of theta here. D theta. And then let's see. What is the, oh, I didn't write down what the square root was in this case. So according to my triangle, cosine would be 5 over the square root. If I flip that, what function do I have? Secant, yeah. So the square root's going to be 5 times the secant. So I've replaced the x, check. I've replaced the dx, check. And I've replaced the square root, check. I've got everything in there. Well, this is exciting. The square roots cancel, right? The secant in the bottom goes into one of those secants in the top. And this 5 goes into that 5 over there. So the only thing left is 1/2 secant, is that right? We crossed out everything else. So I got a 1/2 on the outside, and on the inside, I just have a secant.
So we replace it x at the end.
What's that?
We replace.
We haven't, we still have to come up with an antiderivative.
Yeah.
All right, let's see. Ooh, I don't think did we prove the derivative of the secant? I don't think, oh wait, did we today? Natural log of secant minus tangent? That sound familiar? No?
Raised with the times secant and.
Okay.
No, but you gave it to us during the first term.
I just gave it to you?
Yes.
I didn't justify it?
No.
Okay. Let's justify it. All right, so now we have to figure out what is the antiderivative of the secant. And this is just a really bizarre one. And I want to make sure I got the right method in my head. Let's see. Double check the table. This is one we just kind of got to remember. Okay, here we go. And, yep, there it is. Okay. So, actually, I don't know if it's worth our time.
Maybe a video.
Yeah. It's not really a technique that's useful anywhere else except for finding the derivative of the cosecant. It's just a weird trick. We're just, what's that?
It just has a single purpose on that one.
Yeah, it's just a weird algebraic trick somebody discovered a long time ago. And that's like the only way to do it. So we're just going to go with it. So this is where we're at in terms of our problem. turns out the antiderivative, the 1/2 hangs out. It's just the natural log of the absolute value of the secant of theta plus the tangent of theta. Now we have to reverse substitute. Now that we got past the integral and we have an antiderivative.
Or is that by the 1/2?
What's that?
Times that by, or
It's 1/2 times the natural log.
is that actually the antiderivative, or did you bring that down?
I brought the 1/2 down. Yeah, so this is that 1/2 right there. Yeah, the antiderivative of the secant is the natural log of the absolute value of the secant plus the tangent.
Okay.
All right, so our triangle, I'm going to draw that back in here, has the square root of x to the 4th plus 25 on the hypotenuse. That's theta. X squared was over there and 5 was over there. So the secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant's hypotenuse over adjacent. So that means inside the natural log, instead of a secant, we're going to have the square root of x squared plus 25, oops, sorry, x to the 4th plus 25 over 5. The tangent is nice. That's just opposite over adjacent, so that's just x squared over 5. Put the 1/2 back in front. And we have an antiderivative. That wasn't too bad, aside from the weird derivative, the weird integral of the secant. And the derivation of that isn't that exciting. So, and it's not that useful, except for this one case and the cosecant. All right. One more of these, or try a new type of problem?
I see new
Well,
type.
You say new type, okay. New type it is. All right, so we're going to start taking a look at rational functions. Yeah, so the technique, this is section 4, is that what we're on now?
Yeah.
So section 3.4 is technically called, if I can spell it, partial fraction decomposition. And it's a series of a couple of tricks that are used to take a rational function that's complicated and break it down into some simpler rational functions. So before I show you a couple of the tricks, I just want to make a note about a couple of things. Suppose I had something like 1 over x plus 1 as the function I'm trying to find the antiderivative for. Well, if it was just 1 over x, what would the antiderivative be? Natural log of the absolute value. And this isn't much more complicated. It's just an x plus 1 at the bottom. So its antiderivative is just going to be the natural log of the absolute value of x plus 1. So the constant, the plus 1, that's no big deal. If there was something like a 2x or a 3x or 1/2 x, then the chain rule gets involved and it'd be a multiple off. And we've played with that idea before. What if I had the integral of 1 over x squared plus 1? Anybody remember that one?
Tangent.
That is the derivative of, not tangent, but arctangent. Okay, so I'll show you another trick. Suppose I had 1 over x squared, let's go, minus 4x plus 5. There's a couple of different ways to attack this one. One way is to consider that denominator as a parabola. And a parabola this is the standard form of a parabola in the denominator, but there's also what's called the vertex form of a parabola, which you get by completing the square. Okay, so check this out. If I complete the square on this, well, completing the square says if you have something like, an x squared minus 4x, what would be the perfect thing to be added or subtracted so that you have a perfect square? Well, the trick for completing the square is you take that middle minus 4 and you cut it in half, right? And then you take that thing you cut in half, which would be -2, and you square it. That's the magic number I would like to have there. What did I have instead? I had a 5. So to make this the same as that, I could just say, well, I'll just put a +1 outside there. So now it's still +5, but I've broken up the 5 in such a way that that right there is now a perfect square. It's the square of x minus 2. That's the point of having it right up there. So I get that I can rewrite that. So this now becomes the integral of 1 over x minus 2 squared plus 1. And that right there isn't really much different than x squared plus 1. X minus 2 is just a shift to the right. So the antiderivative of that after completing the square is just going to be the arctan, not of x, but of x minus 2.
So then that +1 just, oh, it's up there. Okay.
Yeah, the +1 is like this +1 right there. That's part of the arctangent antiderivative or derivative. So a lot of what we're going to end up doing is going to be based on the fact that, hey, we know the derivative, the antiderivative of 1 over x squared plus something. Let's see. Oh, did we ever do x squared minus? I believe that we did. Does anyone remember that one? X squared minus 1? Isn't that the hyperbolic arctangent?
Yeah. something like that.
I believe so. Let's double
Yeah,
check.
they're all really similar.
Yeah. Yeah, previous page. This one? Oh, no, wrong one. This one. Yeah. So let's see. It's in here somewhere. Where is it? It's not in the page. Interesting. All right, let's look up hyperbolic functions. Derivatives of hyperbolic functions. 1 minus x squared, which is essentially the same as x squared minus 1. You just multiply by -1. Yeah, so it's the arc hyperbolic tangent. If we have an x squared minus 1, actually be the opposite of that. That's what we end up getting. So we know a bunch of rational function derivatives, so we're going to just rewrite. Okay, yeah. So the derivative of the arc hyperbolic tangent is 1 over 1 minus x squared. So the integral of 1 over 1 minus x squared would be the arc hyperbolic tangent.
Underneath it.
Yeah, so that depends on your x value. If the x values are between 1 and -1, you use the arc tangent, hyperbolic tangent. If they're bigger than 1 or to the other side of -1, then you use the arc hyperbolic cotangent. Yeah, so it is a little bit more complicated than the regular trig ones. We have these catches here, oops, there, and there. All right, so here is another trick to show you. So let's see, the function I just had, 1 over x squared minus 4x plus, let's see, does that work on that one? Is that a factor? Let's do a similar version then. Let's make this a -5, because then it will factor as 1 over x minus 5 times x plus 1. So I get the -5 multiple, and when I add the middle terms, I get a -4, -5x plus 1x. All right, so my claim is that this thing can be rewritten as some number over x minus 5 plus some other number over x plus 1. So we're going to try and find those numbers a and b. What's that? Some college algebra classes cover this idea in terms of rewriting rational functions. All right, so I'm going to take this part right here, and I'm going to get rid of the fractions for a minute by multiplying by the common denominator. The common denominator would be x minus 5 times x plus 1. So if I multiply both sides of this equation by that, let's say this is the left side, the denominator is going to cancel, so I'm just going to have a 1. On the other side, when I multiply by that right there, the x minus 5 is going to cancel for that part. So I'm going to get an a times x plus 1. And when I multiply that by this fraction, the x plus 1 is going to cancel. And so I'm going to get plus b times x minus 5. So that's a similar version of that same relationship, but written as a polynomial instead of a set of rational functions. And it's going to be a little bit easier to learn. Yes, William?
Where'd you get the 3?
I'm multiplying this fraction right here by its denominator. So it cancels.
Okay.
So, yeah, so I'll write that out in more detail. Skip too much on that. So I have 1 over x minus 5 times x plus 1 is supposed to be equal to a over x minus 5 plus b over x plus 1. And I want to rewrite this without denominator, so I multiply both sides by x minus 5 times x plus 1. Which means both of these pieces of the sum have to be multiplied by x minus 5 times x plus 1. X minus 5, x plus 1. And then a whole bunch of stuff cancels. So on the left side, the denominator completely cancels, leaving me just a 1 there. On the other side, at first, in the first part, the x minus 5s cancel, which is going to give me an a times x plus 1. And in the second part, the x plus 1s cancel, which gives me a plus b times x minus 5. So now I just got to play around and figure out what A and B are. And so the way we do that is we pick convenient values for x. So for example, x equals 5 is a very convenient value here. Why? Because it zeroes out that factor. Yeah, so then I'm going to get, if I do that, I get 1 equals A times 5 plus 1. And then I get plus B times 5 minus 5. Right? So that part's just a 0. So now I have 1 equals 6A. So A has to be 1/6. And then I can, what's another convenient value for x to help one? Yeah, -1's a nice one, so x equals -1. So that's going to give me 1 equals, this A part zeroes out. So I get A times 0 plus B times -1 minus 5, which is a -6. So B is going to be -1/6. So this technique is called partial fraction decomposition because I'm taking this one more complicated fraction, breaking up its denominator. Now that means I have to be able to factor the denominator. Once I do that, I break it up into what are called partial fractions. So those are the partial fractions because they only have part of each of the denominator. But the nice thing is, I went from having a square in the denominator to having instead two fractions that are just linear. So let's see, what was A was positive 1/6. So I'm going to get a 1/6 over x plus 5 plus a negative 1/6 over x. Let's see, did I do that right? No, that's an x minus 5, isn't it? Plus 1. So I broke it down into two easier fractions to deal with. So antiderivative, well, for the first part here, 1/6 is just a constant. What's the antiderivative of 1 over x minus 5? Natural log, absolute value, x minus 5. Plus, negative 1/6 is just a constant. And the antiderivative of 1 over x plus 1 is the natural log of the absolute value of x plus 1. So that's one form of the answer. I'm going to clean this up a little bit and show you a slightly different form that sometimes you'll see. 1/6 I can factor out. That would leave 1/6 times the natural log absolute value of x minus 5 minus, because that was a negative 1/6 there, the natural log of the absolute value of x plus 1. Shift this up just a little. Missed. Again. Gotcha. Does anybody remember rules of playing with logarithms? The log of a difference is the quotient of the things inside. So then I can rewrite this again as 1/6 times the natural log of the absolute value of x minus 5 over x plus 1. And then plus c. So why am I showing you that? Well, this first one is a perfectly acceptable answer. That's great. I love it. Okay. But if you were like checking with the integral calculator, the integral calculator might give you that version. And bottom line is, anytime you have a complicated integrand, there's probably multiple versions of the antiderivative. Okay. And what makes those different versions kind of commensurable? Well, this plus C kind of makes them equivalent, even though they might look drastically different. Okay. All right. And I think we don't have time for another one, but I'm just going to shoot. So we're going to definitely need to spend some more time on this. So we've just scratched the surface on what it means to break down a rational function, because there's a lot of different kinds of rational functions out there. And so in section 34, about halfway through, there's what's called the general method. I'm going to zoom out just a sec. So we'll play around with this general method. You can see the whole thing. So the general method is a bunch of different parts. We had an easy problem where it was just a quadratic that factored nice. There are special cases is what if you had, instead of x plus 1 in the denominator, what if it was x plus 1 all squared? What do you do with that? Other thing to consider is sometimes quadratic functions factor, sometimes they don't. True? What if it doesn't factor? If it doesn't factor, you have an irreducible quadratic. And if it's irreducible, that means I is probably involved if you were to apply the quadratic equation to it. So for example, I had one like that earlier. This one right here. This one doesn't factor. I is going to be involved in it. Because if you think about if we were solving this and we brought that 1 to the other side of an equation, we get -1, just the square root of -1. So if I is involved, the arctangent has something to do with it. As I mentioned before, trig functions and I are related to each other in a very interesting way. That was shown in Calc 3. All this stuff I make you wait for, isn't it? So it's like a teaser, the trailer, you know, they do that on the end of episodes.
Metal math classes.
Yeah, pretty much. So we have to take a look at, well, what if we can't factor the quadratic? How do we deal with that? That's what parts C and D are related to. Okay. So we'll look at the different kinds of cases out there. So the rules are, first rule is the degree of the top has to be smaller than the degree of the bottom. If it's not, we do long division. Ooh, yay, we love long division of polynomials. And then aside from long division, once we do get the degree of the top smaller, then these rules A through D apply. And so we're just going to work on trying to apply those rules. Okay. So we get to do some long division, and we get to do some algebra. Some of that algebra involves solving systems of equations. So we're going to actually use matrix math to solve some of those because it's way faster. Okay. So we get to review like half of college algebra to just do this section.
Cool. Nice.
Yeah, so we got another day on this for sure.